When you walk into, well, any modern office space, there's usually this massive humming gray box just sitting right in the middle of a hallway or a copy room.
Oh, yeah, it's always just there.
Right, and you probably walk past it every single day. Maybe you occasionally interact with it. But for the most part, it's just background noise. We tend to view it as, I don't know, a glorified typewriter that just spits out physical paper.
I'd say it's probably the most taken for granted piece of hardware in the enterprise environment. I mean, we treat it like a totally dumb mechanical peripheral.
But if you look closely at Professor Messer's CompTIA plus certification training notes, you realize that big gray box, the multifunction device, or MFD, is actually a highly complex standalone computer.
It really is.
It is sitting right there in the open, quietly orchestrating, well, an incredible amount of network traffic.
Mm.
And the mission for our deep dive today is to give you the ultimate shortcut.
Yeah, to really understand what's going on under the hood.
Exactly. By the time we finish, you are going to be the smartest person in the room about how these ubiquitous machines actually work, how they negotiate with our networks, and most importantly, how they protect or expose our most sensitive data.
That last part is huge.
Oh, for sure. Okay, let's unpack this, because before we can even talk about plugging this thing into a wall or mapping it to a network drive, we have to talk about its brain.
Right, because it's not just a motor responding to a laptop's commands. It possesses its own localized operating system.
Wait, its own OS? Like Windows or something?
Well, not quite Windows. In the world of MFDs, that operating system is referred to as firmware. It's the foundational software permanently written into the machine's non-volatile memory.
Oh, I see.
Yeah, and just like a server or workstation requires regular patching, manufacturers continuously release new firmware versions, to patch security vulnerabilities, optimize memory management, or update cryptographic protocols.
Okay, so it gets updates just like my laptop.
Exactly, but because an MFD is a highly specialized proprietary piece of hardware, the update process is rarely automated.
Right, so you generally have to go digging through the manufacturer's specific technical documentation to find the correct flashing procedure, which sounds honestly like a headache.
It can be. And that manual process is intentional. I mean, flashing firmware means rewriting the core operational logic of the hardware.
So if you mess it up,
Oh, if something interrupts that process, you risk bricking the entire machine. It's totally dead.
wow. Okay, so having an updated operating system on the printer is only the first step. For a client machine to even initiate a handshake with this MFD, they have to agree on the underlying architecture.
Yes, exactly.
Which brings us to drivers. And the source material is adamant about this. You cannot just download a generic driver and expect it to work. You have to match the architecture.
It's very strict.
So if the host machine is running a 32-bit operating system, it requires a 32-bit printer driver. A 64-bit OS requires a 64-bit driver. Why is there absolutely no backward compatibility or mixing allowed there?
Well, it comes down to how memory is addressed. A 64-bit operating system structures its memory pointers and CPU registers entirely differently than a 32-bit system.
Ah, okay.
Yeah, so the driver acts as the strict, low-level interpreter between the computer's kernel and the printer's hardware.
Got it.
If you attempt to pass a 64-bit memory instruction through a 32-bit driver, the translation just fails at the mathematical level.
So what happens? Does it just not print?
Worse, usually. It results in corrupted garbage data or, a fatal system exception.
Oh, wow, so it crashes. Okay, so the architecture has to match just to open the channel of communication.
Exactly.
But once that channel is open, we have to decide what language we are using to actually describe the document. I think a lot of people, well, I used to think this, assume that when you hit print, your computer just rasterizes the image.
Like it takes a screenshot.
Yeah. Takes a giant digital photograph of your screen and just beams those pixels to the printer. But that would consume, an insane amount of bandwidth.
It would bring the network to a crawl.
Right. Instead, it's more like sending an architect a blueprint, right? You send the mathematical code and the printer builds the house.
That is the exact mechanism of a page description language.
Okay, page description language.
Yeah, and the two dominant languages in the enterprise space are PCL, which is printer command language, developed by Hewlett-Packard, and PostScript, which was developed by Adobe.
And PostScript is essentially a programming language, right? Like, you could theoretically open a PostScript file in a text editor and read the geometry command.
You absolutely could. When you hit print, the driver compiles your document into this dense block of vector graphics and text placement coordinates.
Wow.
And what's fascinating here is that the massive heavy lifting of the rendering process, it happens inside the printer's CPU and RAM, not on your laptop.
Wait, really? The printer doing all the math?
Yeah. The MFD parses that PostScript code and calculates exactly where millions of microscopic dots of toner need to be placed on the physical page.
That is wild.
Yeah.
So if you send a PCL blueprint to an MFD that is only configured to interpret PostScript, the machine simply cannot build the house.
Right. It just drops the job.
Which really drives home the point. I mean, if this machine requires dedicated drivers, utilizes its own memory addressing, and spends its day compiling code to rasterize vector graphics, we are basically maintaining a hidden PC.
We are. A highly specialized PC that happens to have a high-speed mechanical paper feeding mechanism attached to it.
Okay, so the brain is functioning. It's successfully rendering PostScript. Now we have to architect the pathways for data to actually reach it. We're moving from internal logic to external networking.
Right, getting the data from point A to point B.
Exactly. So the MFD has an array of physical interfaces. You've got standard USB Type A on the client side, connecting to a square USB Type B or modern USB-C on the printer side, alongside traditional RJ45 Ethernet ports.
Yeah, all the standard ports.
But it doesn't have to just pick one pathway, does it?
No, not at all. A single enterprise MFD can actively route traffic across multiple interfaces simultaneously.
Oh, that's cool.
Yeah, so you could have, say, a legacy terminal hardwired directly via USB, while the machine is also actively listening for jobs over the gigabit Ethernet connection serving the rest of the floor.
And that extends to the wireless protocols too, right? Most modern offices utilize 802.11 wireless operating in infrastructure mode.
Right, where the MFD associates with a central wireless access point, like a router, and clients route their traffic through that hub.
Okay, but let's look at a smaller deployment. Say you have an MFD connected directly to a desktop via USB. To get the rest of the room connected, why not just go into the Windows OS, right-click the printer, navigate to the sharing tab, and map everyone directly to that desktop. Boom, share printer.
Well, yeah, that might function in a small home office.
But not in enterprise.
Definitely not. In an enterprise environment, that topology introduces a massive single point of failure. The desktop basically becomes the absolute gatekeeper for the physical hardware.
Right, because the moment that specific user decides to restart their machine for an update or, powers down at the end of the day, the MFD virtually vanishes from the entire network.
Exactly.
Everyone else is locked out. The hardware sitting there powered on, but the logical pathway is completely severed.
Which is exactly why the industry relies on print servers.
Ah, print servers.
Yeah, a print server intercepts the OS print command, caches the entire job onto its own storage drive, and then feeds it to the printer at the exact speed the MFD's memory buffer can actually handle.
Oh, so that's the schooling process I've heard about.
Exactly. Print spooling. It stands for simultaneous peripheral operations online.
That's a mouthful.
It is, but it completely decouples the client machine from the physical printer. So the user hits print, the job transfers to the server in milliseconds, and the user's computer is immediately freed up to do other tasks.
Oh, so they don't have to wait for the mechanical gears of the printer to finish.
Right. And whether that print server is a dedicated piece of external hardware or just software running internally on the MFD's own firmware, it provides a centralized web front end.
Which is great for the IT team.
Oh, it's essential. It allows an administrator to manage queues, pause jobs, or clear memory buffers without relying on some random individual workstation.
But the source material also highlights a wireless failsafe called 802.11 ad hoc mode. This is a direct point-to-point wireless connection that completely bypasses the need for a router or an access point.
Yes. And if we connect this to the bigger picture, ad hoc mode is brilliant for disaster recovery or specialized environments.
Also,
Well, imagine an IT technician in a massive warehouse dead zone where the infrastructure switches have completely failed.
okay, a nightmare scenario.
Exactly. They can walk up to the MFD, establish a direct ad hoc wireless link between their laptop's network card and the printer's network card, and just push out critical schematic documents. It's a localized network of just 2 devices.
Okay, so we've mapped the network pathways, and the spooled data is streaming into the machine. But eventually, this digital code has to become physical output.
Right, the real world.
And unlike rendering a pixel on a monitor, taming physical objects moving at high velocity is incredibly complex.
The mechanical precision is absolutely staggering. Consider duplex printing.
That's printing on both sides.
Right. As IT professionals, we just check the print on both sides box. But mechanically, the MFD has to pull a sheet of paper from the tray, apply the toner, pass it through a fuser assembly.
A fuser assembly.
Yeah, it literally melts the plastic toner onto the page at hundreds of degrees.
Oh.
And then, using a highly calibrated reversing mechanism, it physically inverts the page and feeds it back through the same path without misaligning the second image or causing a thermal jam.
And the logic controlling the physical paths is fascinating. Take orientation. If a user shifts a document from portrait to landscape, the physical paper does not turn sideways inside the machine.
No, it doesn't.
The mechanical path remains totally constant. The CPU simply recalculates the XY coordinates of the print heads and paints the image laterally across the advancing page.
The intelligence extends to media management as well. An enterprise MFD manages multiple input trays simultaneously.
Right. Tray 1 for letter, tray 2 for envelopes, that kind of thing.
Exactly. But it doesn't just blindly pull paper. The firmware reads the metadata embedded in the print job, identifies the requested paper size and weight, and activates specific sensor-driven pick rollers.
Here's where it gets really interesting, though. What happens when a user ignores their settings and accidentally sends a massive standard letter-sized document, but forces the output to tray 4, which happens to be loaded with, say, expensive, heavy stock envelopes?
Well, the machine's logic obeys the command. It will dutifully attempt to rasterize the entire document across a stack of envelopes.
Which usually results in a mechanical jam, right?
Oh, almost always. But more importantly, it causes a massive waste of physical resources. And managing resource consumption is a critical part of an administrator's configuration.
Because toner is incredibly expensive.
Yeah.
I mean, it is highly engineered microplastic dust.
Exactly. A network administrator will heavily utilize the driver's default quality settings.
So they lock it down.
Yeah. They might cap the default resolution at a standard 600 by 600 DPI and force the spooler to default all jobs to grayscale. If color is absolutely required, they might enforce a color-saving mode.
How does that actually work at the hardware level? The color-saving mode, I mean.
It utilizes an algorithm that intentionally drops alternate pixels during the rendering phase.
Wait, it just skips pixels?
Yeah, it slashes the amount of physical toner laid down on the page by up to 50%, but it still preserves enough edge contrast that the human eye perceives a complete, readable image.
Oh, that's really clever.
Yeah.
It extends the lifespan of thousands of dollars of consumables.
Exactly.
But, toner costs are nothing compared to the cost of a data breach. We have architected this incredible network node. Anyone on the land can route traffic to it. But that introduces a massive vulnerability. Let's say an HR manager needs to print out the quarterly payroll details. They hit print at their desk.
And then the document sits in the output tray, in a public thoroughfare, completely exposed to anyone walking by.
Well, let's look at the mechanics of the file itself. If the data is sensitive, why not just password protect the PDF before sending it to the printer?
Because the encryption only protects the file while it is resting on the file system or moving across the network wire.
Oh, I see.
Once the data reaches the MFD, the machine's CPU must decrypt that file in its active memory in order to translate the postscript into a physical page.
Oh, so the encryption does not survive the physical output phase.
Right. The vulnerability isn't the network transmission. The vulnerability is the physical paper sitting in the tray for 10 minutes before the HR manager walks down the hallway.
So how does an administrator secure the final yard of the physical output? Imagine you're printing payroll details. You don't want to sprint down the hallway trying to beat your coworkers to the printer tray.
Right. The first layer is broad user authentication. By integrating the MFD with the organization's Active Directory, you assign strict rights and permissions.
Okay, Active Directory.
Yeah, you map specific Active Directory tokens to the printer's logic, defining exactly who is allowed to submit a job to the spooler in the first place.
Yeah, because it's tied to Active Directory, you generate extensive audit logs. You can open the Windows Event Viewer and track exactly which user token requested a print job, the timestamp, and the exact volume of pages rendered.
But to solve the physical exposure problem, the document sitting in the tray, the industry developed two elegant mechanisms. The first is badging.
Oh, I've actually seen this implemented. You submit the print job, but the physical machine remains completely silent.
Right, because the print server receives the file, encrypts it, and holds it in a suspended state within the queue. The MFD is aware the job exists, but it will not pull the data into its localized RAM to render it.
Oh, what triggers it?
The user must physically walk up to the machine and scan their RFID employee badge on the integrated reader.
The machine queries the Active Directory database, verifies the physical token against the suspended print queue, and only then does it release the specific document.
Exactly.
You are standing right there as the sensitive document exits the fuser. No hallway sprint required. But what if an organization doesn't want to invest in RFID badge readers for every printer?
Well, this raises an important question, right? How do you achieve the exact same proximity security without all that hardware overhead? The answer is secured prints, commonly referred to as Windows Pen protected printing.
Okay, how does that work?
When a user submits the job from their OS, the driver prompts them to attach a custom personal identification number to the metadata of the print job. The spooler holds the job in suspension.
And then the user walks up to the MFD's physical touchscreen, locates their username in the active queue, and punches in the PIN they just created.
Exactly. The localized CPU verifies the PIN against the metadata, decrypts the spool file, and initiates the mechanical feed.
That's brilliant.
Both badging and pins solve the vulnerability by forcing physical human proximity as the final decrypting key.
It brilliantly bridges the gap between digital security and physical reality.
Yeah.
So we've spent this entire time analyzing how the MFD pushes data out, but it's a multifunction device, a two-way street.
It definitely is.
These machines don't just consume digital code to create physical objects, they pull the physical world back into the digital matrix.
The input capabilities. Yeah, at their core, these devices utilize high-resolution flatbed spanners, often paired with an automatic document feeder, or ADF.
The ADF is a lifesaver.
It is. It sequentially pulls massive stacks of paper across the scanning sensors.
So what does this all mean for the data? I mean, it's essentially a reverse printer. Instead of the CPU interpreting code to lay down toner, the scanner's sensor bar bounces light off the physical page, converts the reflected light into a massive grid of pixels, literally rasterizing the physical world,
Exactly.
and then mathematically compresses it back into a digital file. You just drop a book's worth of paper in the top, press one button, and it instantly teleports into a folder.
No.
But once that massive digital file is created in the MFD's RAM, where does it route it?
Well, that is a critical network configuration. Historically, administrators configured the MFD to utilize SMTP, Simple Mail Transfer Protocol, to basically email the digitized file directly to a user's inbox.
Which is fine for, a one-page receipt.
Sure.
But if you push a 50-page high-resolution color scan through an email server, you run into the limitations of SMTP. Email was not built for large file transfers.
It really wasn't. When you attach a file to an email, SMTP encodes it using base 64, which bloats the file size by roughly 30%. Yeah, so you instantly hit attachment size limits, risk crashing the Exchange server, or just bounce the message entirely.
So what protocol do we use to move massive files efficiently then?
Scanning directly to an SMB destination. Server message block.
Okay, SMB.
This is the foundational protocol for sharing files across Microsoft networks. Instead of encoding the file into an email message, the MFD's firmware opens a direct network socket to a shared folder sitting on a local storage array.
Oh, that makes sense.
Yeah, it streams the raw data at gigabit speeds over the LAN directly into the file system.
And the source notes indicate this routing doesn't have to stay local. With API integrations built right into the modern firmware, an administrator can configure the MFD to bypass local servers entirely.
Oh, absolutely.
When a user hits scan, the machine establishes a secure tunnel and pipes the data straight into external cloud architecture, like an enterprise Dropbox or Google Drive account.
Straight to the cloud.
It's a seamless high-speed bridge from a physical piece of paper to globally accessible cloud storage.
It truly is a marvel of hardware and software integration.
It really is. So let's step back and recap our journey today for you listening. That big gray box is a highly sophisticated firmware-driven computer.
It is.
It processes memory instructions via architecture-specific drivers and utilizes its own localized CPU to compile and mathematically render Adobe PostScript code.
Right.
It negotiates traffic across simultaneous USB and RJ45 connections, handles its own spooled queues, and even establishes direct 802.11 ad hoc networks for fail-safe routing.
Not to mention the physical side.
Right. It manages incredible mechanical precision across multiple sensor-driven trays, utilizes Active Directory tokens and PIN cryptography to secure physical output, and leverages the SMB protocol to reverse print the physical world straight into the cloud.
It handles an incredible amount of our most sensitive data. But, understanding all of those underlying mechanics leaves us with one final and, frankly, somewhat chilling implication based on everything we've covered today.
Wait, chilling. What's that?
Well, we spend millions of dollars securing our corporate laptops. We encrypt the hard drives, install endpoint detection, and mandate complex passwords.
Right.
But as we just discussed, an MFD caches spooled print jobs and massive SMB scan files locally to prevent buffer overflows.
Yeah.
To handle that much data, most enterprise MFDs contain physical, spinning hard drives or solid-state drives right inside their chassis.
Oh, wow. I never thought of that.
Exactly. And most organizations lease these machines.
Oh, no.
Yeah. When the 3-year lease is up, the vendor wheels the MFD out the front door and sells it to a secondary liquidator.
I would guess.
If your IT department didn't pull that internal drive or execute a cryptographic wipe before the machine left the building, your company just handed a liquidator an unencrypted hard drive containing every payroll adjustment, legal contract, and HR document that was scanned or printed over the last 36 months.
That is insane.
We heavily secure the fortress, but we blindly wheel the Trojan horse right out the front door. Shouldn't we be treating them with the exact same security paranoia as our laptops and smartphones? Are we overlooking the most exposed computer in the office?
That is a terrifying realization. You solve the network vulnerability, you solve the physical tray vulnerability, only to expose the hidden storage hardware itself. Thank you so much for joining us on this deep dive into the true complexity of the multifunction device. Next time you walk past that humming gray box on your way to get coffee, I guarantee you will never look at it the same way again. Stay curious.